Started with our last talk of the day. So let's start with a whoop! Thank you guys for coming to EIS for a really great, it's been a really great symposium so far, and I'm really excited to introduce our final speaker, Dr. Cobb, who I've had the pleasure of knowing for a couple of years now. Dr. Cobb is a professor in the Department of Earth and Atmospheric Sciences at Georgia Technical Institute, also known as Georgia Tech, where she is the new Georgia Power Chair and an advanced professor for institutional diversity. Dr. Cobb's research focuses on uncovering the mechanisms of global climate change, both natural and anthropogenic, in order to inform projections of future climate change. Specifically, she uses corals and cave stalagmites to reconstruct tropical Pacific temperature and rainfall patterns over the last decades to millennia. Dr. Cobb has a distinguished publication record, publishing in top journals like Nature, Science, Journal of Climate, and Geophysical Research Letters, just to name a few of them, and she's received over $4 million in grants for her research projects. Dr. Cobb has been a recipient of numerous awards, including the 2013 Sigma Xi Best Faculty Paper Award for her published article in Science, an NSF Career Award, and a Presidential Early Career Award for Scientists and Engineers. And most recently, she's been honored as a fellow at the Brooks Byers Institute for Sustainable Systems at Georgia Tech. She's also been an invited guest at the White House Workplace Flexibility Policies event, I presume during the Obama era. And she has extensive field experience working in a range of environments, from coral reef ecosystems on Christmas Island and Island atolls to caving expeditions in Malaysia and Borneo. Her research has been featured on the front page of the New York Times, NBC's Today Show, and the Showtime documentary Years of Living Dangerously, which even my mother watched. Lastly, Dr. Cobb actively engages with the scientific community through her Twitter account, which has over 3,500 followers, her research blog, which gathers more than 200 views a day, and her annual trips where she brings her students to Capitol Hill to meet with Georgia lawmakers. So without further ado, please give a hand for our final speaker, Dr. Kim Cobb, who will be discussing climate science and public policy, a shifting landscape of risk and opportunity.
For making it to the very end of this long day and very fun-filled and educational day. And I want to thank the organizing committee for inviting me to present here. I am not an ecologist. I'm not going to pretend to be. I will promise some death, and destruction to echo some of our earlier speakers' talking points. But first, I really wanted to start by giving you a little bit of a context for how I enter this space of climate science and climate policy from my scientific grounding, so my latest work and how I've approached this and where I've been up to date scientifically. And then I'll end my talk with some thoughts about where I'm going in the future, scientifically as well as non-scientifically, and the roles that I believe that those play. So at the top of this, I have to acknowledge funding from NSF and NOAA, which have sustained my research program over many years. And then most notably Georgia Tech for recognizing me with all of these wonderful endowed professorships, which enable me to grow my program and be ambitious and be brave and try new things. And also my wonderful students, most notably Pamela Grove, whose dissertation work I'm going to present as a portion of my talk today. This is largely based on my coral reef work, but I do a lot of work in Borneo too, so that talk about deforestation and work that at the forest level is very close to my heart as well. So this is where I start. I entered the field of climate science as an undergraduate researcher, knocking my head against one of the most perplexing and fascinating aspects of our climate system, the El Niño Southern Oscillation. And I decided it was a topic worthy of a lifetime of study, and as indeed, of course, we haven't answered near enough questions as we have to ask about this system. So I'm sure it'll be worth another lifetime of study for me going forward. And this was a very seminal year last year, 2015-2016, saw the largest El Niño event on record roll through our planet. It really brought death, destruction to a lot of different systems, both human and, of course, ecological, as I'll discuss today. And so it's really going to be the launching point for some of the work I'm going to show you in terms of motivation. And this is a history of this phenomenon, the El Niño Southern Oscillation, over the 20th century as recorded in central tropical Pacific temperatures. And you can see that it has recurred every so many years. It goes warm and then it goes cold, and there doesn't seem to be much rhyme or reason to it, and we can pretend that we understand some of the fundamental physics, but really we have only about a 6-month predictability on this natural climate phenomenon that wreaks so much havoc on our planet and our social structures and ecological structures. And so, of course, at the last part of this record, you will see the 2015-2016 El Nino event here, peaking out at about over 3.2 degrees Celsius in the central tropical Pacific in terms of ocean anomalies. Really the largest ever, the maximum extent of temperature ever reached in that region over the instrumental record of time. And it follows on several other major events, most notably 1997, 1998, 82, 83, 72, 73. We have a cluster of very large El Nino events occurring in the late 20th century, which obviously kind of begs the question that everybody's been asking me for so many years now, is climate change driving intensification of this natural climate cycle? As we believe now as climate scientists that climate change is driving so many other packages of climate extremes going forward. So this is a very pressing question. If I can answer this question, I can pretty much, close the book on my career and die happy. This is the level of difficulty of answering this question when you're dealing with this kind of variability. You can see that this is going to be a tough question to answer. We have very few events over the instrumental record, and they're all over the place, and one might be tempted to draw a trend line through that, but trust me, you would not be statistically significant. Coupled with the fact that over the instrumental era, we have very, very few direct observations of marine temperatures going back to the early 20th century. So this is how I prefer to think of the instrumental record of temperatures over the 20th century, where we get hazier and hazier as we approach 1900, really fall off a cliff at about 1900. We shouldn't really pretend that we have much to say about anything in terms of Central Pacific temperatures prior to that time. So we're really locked into about 50, 60 years of very good temperature observations, really adding some even more level of difficulty to this problem. So as I pose this to climate scientists, we can either wait 100 years to answer this question when we have many more realizations of these greenhouse gas El Nino extremes, or of course we can turn to the paleoclimate record, archives the recording ocean temperatures through time, and allow us to probe the history and statistics of this phenomenon going back many centuries or many millennia prior to the rise of greenhouse gases. Of course, this is my only option. I'm going to put my whole career on this option too. I will not be alive in 100 years. So we have to push forward with the kind of archives that we have right now to address this question. And this turns out to be a lot of fun. So I go to the Central Tropical Pacific and I dive in these sites where these ocean temperatures are locked into coral skeletons. I'm going to show you just how well they do in a second. This is me drilling a massive coral that grows about 1 to 2 centimeters per year. So providing about a monthly estimate of ocean temperatures back through the lifetime of this coral. This is a pretty small one by coral standards. This will be about 50 years of information locked into a core that's about 1 meter in height or so. And so we can use the reefs that are occurring right now underwater to probe the history of ocean temperatures back about 100 years or so. Obviously, we can't go back millennia using live corals because you don't have corals that are alive for many, many, many centuries. Only incredibly rarely do you have that. And so what my career has been based on is really trying to probe this so-called fossil archive of corals here, which are corals that are washed up onto the beach over geologic time, and they just sit there waiting for me to go sample them. The difficulty here is that the coral lying on the beach looks like a gray rock to you, to me, to everybody except a mass spectrometer that can tell the difference between a gray rock that's 50 years old and a gray rock that's 5,000 years old. So we use uranium-thorium dating to probe the exact age over which this coral grew. And then we can drill these holes in these kind of cores and get 15 to 100 years at a go, distributed back as far as we have these archives available. In this case, at these islands I work in the Central Pacific, roughly 7,000 years or so. So this is what it looks like when you cut these corals open. So much like tree rings, they grow quite quickly every year. They actually grow a lot faster than trees. And so we can count back the layers of calcium carbonate that the coral has accrued, and then we can draw a sampling transect down this, and we measure the change in oxygen isotopes in the coral skeletal geochemistry. And the oxygen isotopes are fractionated with respect to the 18-16 ratio as a function of the temperature that the carbonate is formed in. as well as the sea surface temperature, as well as the starting oxygen isotopic composition of the seawater that the coral is growing the calcium carbonate skeleton from. So basically you have your starting point, and then as a function of temperature, you change your coral oxygen isotopic content. Now this effect, the temperature effect, is actually something we could reproduce very, very well in the lab. It's a kind of a function of Gibbs free energy. It's something that can be theoretically determined, and we can measure with enough precision to reconstruct temperatures to better than 0.2 or 3 degrees Celsius, which turns out to be good enough for our purposes at chasing down El Nino events. And this one is something that we can measure in the modern day, and we can relate that very closely to salinity, and that's a function of the change in evaporation and precipitation of the surface ocean. I'm not going to get too technical on that. I could give a whole talk on that. I'm very obsessed with that. But moving forward, how do we look at this over an El Nino event? We can actually understand the changes that are occurring in the Central Pacific across El Nino events, how that will impact the coral, and then we can actually go test that, recovering cores that accrued over the recent temperature extremes related to El Nino. So over the 2016 event, the one we just had, you're looking up here at a map of sea surface temperatures in the tropical Pacific, and here you have a big swath of warmer than average temperatures across the central and eastern equatorial Pacific, kind of the classic signature of El Nino. My research sites are right around this black circle, indicating that these sites get much warmer than average during El Nino events. Now down here, we have the piece that's related to the change in seawater chemistry, the oxygen isotopes of seawater. In this case, we're using outgoing long-wave radiation to indicate that in my research site in conjunction with a big blob of excess precipitation, it gets much rainier at my site during El Nino events, driven by those warm sea surface temperatures than average. Usually my research site, Christmas Island, is a desert. There's like 2 palm trees growing on the windward side. And during El Nino events, you see this huge green out across the entire island as this place becomes basically a swamp. So it's a very marked difference. And so it gets rainy and it gets warm. Both of these things, it turns out, drive the coral oxygen isotopic composition down. So it's driven down by temperature, which is an inverse function of temperature, and then it's driven further down by this rainfall signature that we get during El Nino events. And so we have a great proxy for these El Nino events and a great location to apply it to. And this is how well we do in reconstructing ocean temperatures at this site with coral oxygen isotopic records. So here I'm showing our calibration over the last 30-ish years, 30, 40 years, and what you're looking at in this panel is a plot of, this is sea surface temperature in gray, or in particular the satellite-derived index. You can hardly see it because it's overlain by all the different modern coral records of oxygen isotopes that we recovered from this site over my career, and those are plotted in colors. I think there are 8 different coral cores here, including my work with my brilliant undergrad, Jim McCrummer, plotted there for over the last El Nino event from cores we recovered in April. So this is how well we do. It's actually quite amazing that we have the ability to reconstruct temperatures at this very remote site where we have so little data from the instrumental era. And of course, this isn't particularly great. We already have sea surface temperatures from this period. But of course, when you go back in time, many centuries and millennia, now you can reconstruct El Nino events that we have never seen before as humans, and we have never documented. And that's where this gets interesting, to push this way back before the greenhouse gases came up. And I want to say that this is a combined effort of many different kinds of students working over a very long time to get this plot together for you. So this is interchangeable with SST, and so we're going to use this going back. So this is a plot of Christmas Island sea surface temperatures inferred from coral oxygen isotopes over the last millennium. And so each of these pieces has been run at monthly resolution. These are fossil corals recovered from beaches, uranium thorium dated, run every millimeter for oxygen isotopes on my mass spec in my lab when it's working, which is very difficult to keep it running. But this is what we've been able to amass over many, many years of efforts. I hope you're impressed. So, God, bad way to plot like 10 years of your life on one plot. You know, give it a second here. So what you're looking at here is the oxygen isotope values on the y-axis, and the plot is such that warmer is up here and cooler is down here, according to the calibration I just showed you. And so what you can see here is that things go around and climate changes. El Nino spikes happen, and La Nina, the cool phase spikes happen. And then we get to the 20th century and the baseline starts to head up. And then we get to this last little tick right here, exceeding minus 5.5 value is the peak of the 2015-2016 El Nino event. So this basically indicates that there's been a shift in the baseline of ocean temperatures related to greenhouse gases. It's not very linear, it's quite complicated, and that there's also El Nino events that are taking this temperature index up to higher values in the recent past. And so we might look at Palmyra, which is a neighboring island. So this is at 6 North, just north of Christmas Island. I've been working across the entire Line Island chain for my career, trying to amass more and more data. And this is a Holloway plot, 20 years of data on a single plot. But let's take a second here. Right, good. So this is over the last millennium from Palmyra now. So many, many different corals. There are over 20 different coral records plotted on this plot. Some of them overlap in time, so we splice them together to get these monster sequences like this beauty here, 310 years of continuous information from the Central Pacific in monthly resolution. So this is a very, very unique time of record that we're pushing here. I always get the question, how long would it take you to fill these gaps? I'm like, I don't know, how much money do you have? So, yeah, I will do it. If you want to give me that money, I will do that for you if you're that interested. So this is cool, and we'll continue to do this as we can, but we've already learned some of the very key lessons from this kind of study. We've learned that, climate warms and it cools, and we have El Niños and La Niñas, some of them quite large. Some of the largest El Nino events in this sequence are actually right here, during the so-called Little Ice Age in the 17th and 18th centuries. And then, like the Christmas Island data, we see this dramatic change in the baseline of ocean temperatures during this time period, with these last El Nino events kind of again taking us into way uncharted territory of absolute ocean warming during this interval. But the real question is the variance of these time series changing with respect to the El Nino system? Again, this is the question that has driven my entire career to date, where I started as an undergrad, where I will die having probably not answered satisfactorily enough, but it will keep me going and keep our community going, because this is a very important question for societies and ecological systems as they face a changing climate. And so to answer this, you really have to dig in the statistics of these time series, because you can't see by eye whether the variance of a time series like this is changing through time. So we have to probe the statistics by isolating that component related to the interannual variability of El Niños, specifically, kind of remove all the other variability that's happening at the lower frequency and ask whether these statistics are changing. And so if you combine our entire data set now, over 7,000 years of stuff that we've amassed, most of this was published in my 2013 science paper, but Pamela Groth, my new PhD student, she's about to finish a couple months. She has doubled the amount of data that I published in 2013 and has really brought the level of rigor that we need to say what I'm about to say in this talk. So we have amassed over 2 millennia worth of monthly coral data scattered throughout the last 7,000 years. And what I'm going to do for you in the next plot is only plot the variance of the time series on the y-axis, and it's going to go back 7,000 years. And so you can see how the variance of each sequence is going to change through this long, kind of relevant geologic period. And this is a lot to take in. This is plotting my entire career here. Yeah, and everything on the one plot. But this is what we've been going for my entire career, is to get to this point where we can ask this question and get an answer. And so just to orient you how this plot works, this is time now, if you will, and this is going back 7,000 years. We're in thorium-dated corals. And then on the y-axis here, we have the relative change in the standard deviation of this interannual climate phenomenon that is so powerful at this particular site in the Central Pacific, and these sites are so sensitive to that. And so I've filtered the data, and I've calculated the strength of this interannual fluctuation, and I'm plotting that relative to 0, where 0 is the late 20th century ENSO variability as captured in that calibration interval that I showed you when I showed you the modern corals, what I call the modern coral stack. And so what you can see here is that above the 20, if you're above this red line, then you're stronger than the El Nino variability of the late 20th century. And if you're below the red line, then you're weaker invariance than the late 20th century El Nino system. And we all lived through the late 20th century El Nino system, so that kind of, we had an intuitive understanding of what that world looks like. Some of us a lot more than others, having stared at a lot of time series myself over that period. But what you can see is that most of the pre-industrial coral sequences are falling way below the late 20th century ENSO variability. Okay, and so when we sent this first to science, and we didn't really want to make a big stick of this, we were more interested in kind of the paleo-related signals in this data set, and the reviewers said, no, you really have to talk about this story. This is potentially really important. At the time that we published this data set in 2013, it was only half of the points that you see here. And so you can imagine how tentative and scared we were to say that there may be a change in El Nino variance related to this data. And now Pam is about to publish this data set this spring in its entirety, which is as it stands right here on this plot. And we can actually say with statistical significance that there has been a change in 20th century El Nino variability relative to this broad, incredible amount of pre-industrial data that we have from the fossil corals. And I'm not going to go through all the statistics of that. It's very complicated kind of Monte Carlo simulation of the kind of undersampling that we get. We use these windows through time, and we can do this Monte Carlo thing with different nulls, and I can really go into those details if you want. But suffice it to say that her analysis using this statistical significance testing with this appropriate choice of diverse nulls and Monte Carlo simulations yields the inescapable fact that the observed difference between all of the pre-industrial coral data and the late 20th century coral data is way above the statistical significance of about 99%. So we're like at the 99.9 level in saying that there's a fundamental difference between the variability in the late 20th century coral sequences and that of the pre-industrial era. And so that conclusion will stand. There's almost nothing we can do to change that conclusion, sort of like quadrupling our sampling size at this point. The signal is too large to erase just by throwing more data at this problem. So going forward, I'll have to do something different with my life, maybe, or change sites and test it again, of course. But I always love to go to another site and explore something. So basically, what we can say here is that it's virtually certain, and there's an asterisk here, and can you read that fine print? You can't, that's too bad. Anyway, it's virtually certain that the observed distribution of coral variance that we see reflects a change in ENSO properties. And this is basically driving the conclusion that we make, that ENSO extremes are becoming larger with climate change than they were previous to the pre-industrial era, the industrial era. And this really comes in line with a lot of other studies that are cropping up in the last few years, pointing to the same conclusion. I list some of them here, and this is kind of beyond the scope here, but I am involved most notably with this paper coming out of China using Taiwanese tree ring records of the isotopes in those. It's going to say very similar conclusions to what myself and my grad student are going to be able to say. So this is an emerging body of evidence for El Niños getting stronger. Now let's go back to 2015. Let's take ourselves back to what was going through my lab and our lab's work and going out in the field during what was to become the largest El Nino event of the instrumental era. So this is November 2015. We were going down there on expeditions starting in August 2014, and every 6 months since August 2014 we've been going down there, looking at the corals, taking a lot of photographs, installing observational arrays for measuring salinity and temperature and pH and turbidity and all this stuff down there. And this is what happened over the course of the time that I was working at this site very intensively. We knew an El Nino was coming, so we had the benefit of getting down there and installing a bunch of equipment. And this was from the NOAA Coral Reef Watch product that shows the temperature stress that the Northern Line Islands experienced over the course of this last El Nino event. So you're looking at 2015, you're starting into bleaching territory in June of 2015. You're already at bleaching alert level 2. They should have had an alert level 3 and 4 and 5 for the temperature stress that my island experienced across this El Nino event. It was an unprecedented level of temperature stress, peaking out over about 28-degree heat weeks at its maximum stress. The bleaching threshold is about 12 to 13. So it was huge, and it went on forever, pegged at maximum temperature stress for a period of 9 or 10 months before it subsided, not until June of 2016. So that's almost a year of bleaching level stress at my research site. And we were there in July of 2015, November 2015, and April of 2016, and again in November. So, and again, I'm going back again this fall. So what happened to this reef? Well, first I need to show you a picture of what this reef was like before. So this reef is very remote. We have an island that is, and it's the largest coral atoll in the world. It's inhabited by 7,000 people. They live in a very concentrated little strip on one side, and we use dive sites across the entire island, some of which are only accessible by boat ride of 4 hours. And so some of these reefs are very, very, very pristine, and they're just sitting there, being bathed in Pacific waters, and this is the kind of thing that we see when we go diving there. We see very diverse assemblages. We see near 100% coral cover. I know you're not many coral people in this audience, but this is a picture of a very happy reef. When we went back in November of 2015, remember temperatures spiked in November, so it was about 3 degrees Celsius warmer at my research site. It had been warm at bleaching thresholds at this point for about 6 months. And here you can see the bleached corals throughout this particular site, the same site that I just showed you. So all of these corals are bleached, they're photosynthetic algal symbionts have left them or they've kicked them out, and they are ghastly white, and they're just waiting for temperatures to come back down so that those algae can come recolonize the corals and they can go on their existence. But right now they're literally starving, and they only have about 2 or 3 more months before they will die as a result of this bleaching. So you can't stay bleached forever, just like you and I can't go without food forever. So this is the ghastly site. During this November campaign, we saw that we've lost already 100% of some species. They're more fragile branching species that are so temperature susceptible. We're already 100% dead at our research site. So I have that. Oh, here's that. Here's one of those pictures. So these are big Acropora colonies that are all, this is November, all of these brown things are already covered over in red-brown algae. They have been long dead for weeks and weeks and weeks by the time we got there in November. So this is us doing some sampling transects. I'm not an ecologist, so you can imagine me with all of this equipment down there and tape transects and cameras floating all over. It was a real learning curve, let me put it that way. So we went back in April, this is what we found. So the worst had come to be. The absolute worst case scenario, you sit at your desk, back at Georgia Tech, and you see the temperatures, and you think it's going to be bad, but you think that there's probably some way that nature's going to surprise you, and then you get there, and it just died. Everything died. We lost over 85% of the reef between November and April, and we only had a survival rate of about 3 to 5%, depending on how you count that. Some sites had no surviving corals, some sites did a little bit better. This is the view of the coral reef that I'd shown you previously. So here we see all these corals that are actually, you can see their structure, but they're all dead. They're all covered over in this kind of fuzzy brown red algae. This vista is just a graveyard of corals. So what do we do from here as scientists? I've been working very closely with a team of ecologists. I'm trying to learn some new tricks. Most notably, Julia Baum, my colleague at University of Victoria, has been conducting research at the site for 7 years now, and she was there for November and the April campaigns. We all saw this together. We're continuing to process it. We're working with Ruth Gates in Hawaii, who's trying to use both natural and artificial laboratories to design the supercorals of tomorrow that could be temperature resistant and resistant to acid conditions. So she's trying to bioengineer future corals, basically. And my money's on that because of what I saw in 2016. And then a host of other kind of oceanographers and climate scientists interested in this problem. So we'll keep this up. But this was a profoundly kind of big turning point for me as a scientist and as a human. And I think it's one that we all need to consider right now as well, because we are seeing the news coming back from the Great Barrier Reef, of course, last week and this week. Vast sections of the Great Barrier Reef bleached and died last year, and new data coming from the Great Barrier Reef indicating extensive bleaching this year as well. I wrote this blog for the El Nino blog, kind of before and after blog of the bittersweetness of having been an El Nino chaser your whole life, waiting for the event that's going to bring home your science in such a profound way, offering you the biggest signal you could ever hope for as a scientist. And yet, the very archive that you're using to record climate is killed in the climate signal that you're chasing. Really a tectonic shift in my life as a scientist. And so this is where I landed on the cover of New York Times. a grim entry into that world as well, and a big press blurb over what became a global-scale coral bleaching and mortality event, unprecedented in scope, culminating in April and May. And this is just indicating the grim news from the Great Barrier Reef this year. Terry Hughes published this just a couple weeks ago, indicating that in 2016, of course, up to 30 to 60% of the Great Barrier Reef bleached in different sections. This is the 2016 bleaching levels. All the red is greater than 60% of the corals on those reefs in bleaching conditions, and this is green, less than 10%. So a very vast portion of the Great Barrier Reef bleached. This year is looking no different. And for those of you, all of you ecologists, the really important thing to me from this study is that the protected sites, those sites that Australia had cordoned off from all kind of tourism and fish takes and all the horrible things that can occur to reefs, sedimentation and river runoff, those suffered just equally as the unprotected sites for the bleaching levels that they observed across this survey. So all of the work, all of the stakeholder engagement, all of the laws that had been passed to protect these sensitive portions of the reef, these gems of our world, did not protect these reefs from the ravages of rising ocean temperatures, and nor they will do so in the future, of course. A profound lesson. You can run, but you cannot hide from the inescapable fact that these ocean temperatures are going to keep challenging these reef systems going forward. So, and then, not only did I have to suffer through 2016 as a scientist watching their entire study site die, the archive that they've used for 20 years to record temperature, die, facing the prospect of never being able to drill another coral record from that reef to generate temperatures. The whole thing died. That's the death part, right? Then I had to suffer through November. So, 2016. A hallmark year for me as a scientist, and I was on Christmas Island when the satellite was loading, CNN.com, on November 8th. It's Trump. I only got halfway with it, it's Trump part when I just lost it. I had to go for a very long walk. And we stayed in denial for about 8 days as a group, just said, folks, we don't have a choice. We have dives every day. We're 50K into this field expedition. Your safety is my #1 concern. If you don't think you can do this, tell me. Totally understand. Sit in your AC room. Glue yourself to the internet for what it's worth. Little 2 kilobytes per second, right? Or come out with me. Let's try to get through this. Let's try to do our science. Let's try to pull it together. And everybody did. I was very proud of my team for doing that. I was definitely myself in some kind of altered reality, absolutely tripping on science, trying to not think about anything that was happening back on mainland. Even I was taking press calls from all of my press people. How are you? How is it horrible to Trump? And trying to keep it together. And so I did. But obviously it began about a 2-month period when I say that it was a mental health crisis would be a gross underestimation of what happened to me in November and December. So that's the black slide here. I think it's a chapter in our society, in our Anthropocene, that will hopefully mark one of profound beginnings and not the beginning of the end of our civilization. And so I want to just mark that for me, how I came out of this was remembering some of the lessons we've heard about today, that you can only quantify resilience in the face of stress. And so what does this mean for all of us as scientists, as people who care about natural environments and the fate of our planet? So this was me looking somewhat askance at my first ever political rally in December during the fall meeting of the AGU. I got a call 24 hours before this rally and said, "We've had a speaker drop out. Can you speak at this rally?" I was like, sure. Well, I'm prepping my talk and like dealing with my posters and like going to all these things. I'm like, sure, I'll say a couple things. I really had no idea. I really had no idea. Remember, I was still in this like hazy, feeling my way thing. So that's me looking a little puzzled. There's Naomi Reske's talking right in front of my slot, and I'm like, what am I going to say? I haven't prepared a single thing. This is not going to be good. And I like his sign back there, ice has no agenda, it just melts. So these are all scientists from the AGU. A meeting of over 38,000 scientists, and there were about 50 of us on the steps at that rally. So just to put a marker on where our community begins a process of hopefully getting better at this. This is kind of the lowest point when you have a rally like that and 50 people out of 38,000 show up. You know you're in trouble. Here's me speaking. I somehow mustered some words. You can go listen to them. I'm not going to play it here. I would be very embarrassed and horrified. But check it out. I'm trying to find some words. It was totally ad-lib. It was completely unprepared. And I basically said, why are there only 50 of us here? We have a job to do. It's going down, people. It's going to continue to go down. And this is what I brought. This is one of my best quotes that I mustered that day on the fly. For too long, we have as scientists relied on our data to do the talking for us, and that strategy has failed miserably. So again, I put it to us that as much as we love science in this room, because we love science in this room, we owe it to the practice of science, we owe it to the planet that we love, to throw off the shackles that are holding us back and think about what it means for us to engage at all levels and at all scales. And then this happened. I went to DC to participate in the largest march ever recorded in DC. Very proud and honorable and humbling moment for me as a human, as a woman, as a mother, as a climate scientist. This is me that day, wearing my little pussy hat. Very happy because on that day, I realized I wasn't alone. I might have been one of 50 people standing at the stairs of this science rally AGU, but I was one of a million people marching the streets of Washington saying, I've had enough. This is the line. I'm not going to cross this line, and we'll let you cross this line. We are holding our ground. So I was very happy and enervated that day, and it's carried with me to this day. And this is the sign I'm holding, is a sign with a sticker from the 500 Women Scientists Group, and they have over 17,000 signatures. You can check out their pledge, but it basically says, we are women, we are scientists, and we're drawing the line here too. And we have, again, I've since joined this organization, I'm on their board now. There's 100 pods over the entire United States. I lead one in Atlanta. You guys could start one here in College Station. It's a wonderful organization. They coordinate letter writing campaigns and op-eds and all kinds, doing patches for the Science March coming up soon. It's really fun. And this is something I just got involved with, an open letter to Scott Pruitt, basically condemning his remarks, saying that CO2 was not the primary driver of recent warming. And so this was signed by Nobel Prize winner Mario Molina, as well as 29 of my other esteemed climate science colleagues, and published an open letter and carried by some press outlets. I was very proud and honored to be a part of that and continue to agitate at the federal level when I can. This is an organization I'm often involved with. If you're interested in getting involved from a federal policy level, Citizens Climate Lobby is advocating for a carbon fee and dividend model where they charge the carbon at the point of entry into our economy. We all pay modestly higher prices. That tax goes into a coffer in DC labeled carbon fee. And at the end of the year, that coffer is divided by the number of every American, and checks are sent out to every single American. Those people who drive 5 Hummers and own 5 houses are subsidizing my good choices as a low-carbon consumer. Basically, I get paid, as I should, properly for the choices that I make to help our planet. And then locally, this is what I'm doing on January 1st. This is part of my recovery, my own personal recovery, that's what I call it, recovery. And this is my horse. So going back to the comment about we all need to get on our Transams and get back on our horse, this is basically our modern-day equivalent of a horse. So I started biking to work every day. It took me 14 years to make that change. Yeah, okay. All right, so just let that sink in for a second. Here I am in my full suit. Here's me after. Here's me before. My full suit with 4-inch heels. I love fashion. I just bike to work like this. Yeah. People think I'm crazy, but it helps me. What it does, people, on Twitter, people go crazy. This is not going to save our planet. It's so stupid. Well, it doesn't really matter what it does for you, because I know what it does for me, right? And so we have to get into this modality where we realize that everything that we do is to keep us breathing through this process every day, right? And know that in the end it may add up, but even if it doesn't, it helps me. And that's actually what matters so profoundly. And this is also because I got involved with, so I started biking on January 1st, and 2 weeks ago I launched this crazy petition to advocate for my city and make a bike lane, and that whole thing, city planning. I'm now sitting on the new Stakeholder Advisory Council for the City Planning Board. Don't ask me how I'm going to fit that on, but it matters to me. All of a sudden, this stuff matters, the small stuff matters. And I hope it begins to matter to all of you too, because it's by doing this that we inoculate ourselves against the depression that was so pervasive in this room across all of our talks today. We have to. We have to find a way. This is my way of finding a way. You can find your own way. There are a gazillion avenues to get involved. This is my house. Yeah, I didn't have these signs before January 1st. Okay, there was just a dark cloud over my house. And now I have my John Ossoff sign and all this other stuff. And it helps me remember that I care every day. I care. And this is something I started as a new initiative for the diversity program I'm involved with, which is the first ever campus discussion for queering STEM. We call it queering STEM. I'm very proud of it. And we're convening a group of students and faculty and postdocs to start to talk about how we can provide resources and community for this group that is also under unique threat in the current administration. And of course, I'm speaking at the March for Science in Atlanta, which I encourage you all to take part in. It's a great, great movement. I think they have a great purpose, and we're all learning as we go in this new field of activism. But this is a great channel to voice our stake that we have as scientists and of future policies. So just to end, I wanted to talk about some do's that I've learned. So do stuff. Do a lot of different stuff. Do whatever you feel you have time for, and then do a little bit more. Because it matters right now. It may not matter in 20 years, but it matters right now. I can tell you that much. And what happens right now may very well shape 20, 50, 100 years into the future. And not just for science and our own self-skins and our own funding, but the entire course of sustainability on our planet. So when you do stuff, talk about it, right? You can just gain your own recovery, your own medicine. That's very good, and that's a good part of why I do what I do. But I also have a very active social media presence. I didn't cultivate it for what I'm doing with right now, I'll tell you that much, but I'm certainly leveraging right now to spread hope and messages of engagement on the part of scientists like myself. And so this is a kind of, what we call hashtag hijacking, dressed like a woman, and this is just me doing my thing underwater. And so there's a story to be told here. All of you have amazing stories to tell. Incredibly engaging stories about science and its transformational capacity and its visceral just awesomeness. So I hope that you also think about how you can tell your stories to maximum effect. This is all storytelling. Stay informed of current events and educate yourself about solutions. We're really good at identifying problems. We heard like 50 zillion today, right? We have problems at small scales, problems at big scales, problems at spider scales. We have all kinds of problems. But where are the solutions, right? So we have some other people, some other part of this campus probably thinking about solutions. Well, scientists can be part of the solutions. They must be part of the solutions, something that Dr. Wu said so eloquently. So if somebody comes up to you and says, oh, good problem, Kim, corals are dying. What do we do about it? Are you ready? Are you ready to say something? Is it going to be informed? Can you help your fellow Americans understand that there's a way forward, and what that might be, and what scale that has to be accomplished at? I challenge you to think about that. Take some policy classes, stay informed of these things. Be brave, take risks. Trust me, it was not easy to stand up at that rally and just blah blah for 3 minutes about how we need to get engaged here. It was really scary. It'll be scary to stand up there as a science march to even a bigger audience and say whatever I'm going to say. Okay? But if we don't do that, nobody else is going to stand up there and defend science, I guarantee you. So it's on us. It's on all of us to do that. Take care of yourself, my goodness. If you're going to do this in earnest, it's going to be punishing, it's going to be humbling, it's going to be depressing. It's a lot easier to sit in your office and try to submit your next paper. I guarantee you. So take care of yourself, treasure yourself, find some inner strength, find some extra reserves. And then please take care of each other. When somebody does get up there and say something in defense of science and take a risk, don't say, oh, well, they're just that person. They're just really good at that. That's not me. Like, power to them. No. Write them an email. Say, thank you so much I appreciate you speaking up for science. Do you know how few people wrote me after I stood up for science and spoke at that rally? Maybe fewer than 10. And everybody thinks, oh, somebody else is going to thank her. No! Thank people for speaking up and standing up and being brave in this era. Show us that we can have community, that it matters. And then some don't. Don't be afraid to mess up. I've messed up so many times in this space. I've fallen flat on my face so many times. That was a stupid tweet, oh my God. Or I really pissed off that person, and me too, or now I have all the haters and the crazies on me. I must have done something wrong. Don't mess up, we've all been there. And don't sit this one out. Don't do that. Don't do that. If we will pay too high a price. Trust me. We are paying a price today, and we will pay a greater price in the future, and our planet will pay the biggest price if we, each one of us, choose to sit this one out. Don't lose hope. Most important, don't lose hope. The solutions are at our fingertips. Trust me, they are. We don't lack the capability to find solutions at scale. We lack the political will to implement them. And that's where each one of us has a role to think about that and let that sink in. We owe it to these people. These are my kids. So they're going to inherit this world. Your kids are going to inherit this world. We owe it to them. Thank you.
I don't know about you guys, got emotional.
I'm okay, so I can take a question, I promise.
We have about 10 minutes for questions for Dr. Cobb, and just, I didn't preface this, but we are going to have a happy hour with the speakers and restaurant after, so you'll have more time to chat with the speakers. But questions now, please.
I have a couple of questions, but they're mostly vague. And that is, are people measuring the oscillations in other oceans using these corals, and then are they increasing, do they have increased gradients as well in temperature over time, or is it something endemic to El Nino? And then I guess in a related question is, these varieties, you know when they came from. And I assume they're mostly varieties, not Crocra or Salapra, but where did they come from? Are they in a fringing reef, or are they on a reef crest, or are they from deep down, or we have no idea? Because it seems to me like the ones that have degraded would be from near shore, and the ones that are still around on the shore might be older and deeper. So I guess there's a bunch of questions.
Yeah, I mean, I think so the most general question, there are a handful of people who do this kind of work for a living in terms of reconstructing Huntington corals, probably like 20 across the world who are working in the space that I am. I definitely have amassed the largest coral collection in the world. I'm definitely, way on the whack job scale of that. But in terms of other oscillations, so there's a very small El Nino phenomenon in the Atlantic Basin that people haven't really been able to push past the instrumental record yet. The Indian Ocean has its own kind of El Nino thing, and the Indian Ocean dipole, and people haven't been able to amass enough of a record. So I guess I'm trying to provide a blueprint in my own work for how to expand these studies of changes in variance in ocean temperatures. The most kind of frequently applied place where you find the coral work is for looking at decadal variations back through time and trying to reconstruct the spectral signature and the spatial footprint of decadal variations like the Pacific Decadal Oscillation. I've kind of left that for the studies of extreme events related to El Nino, but I guess what I'm trying to do with my own work is prove that we can truly extend the instrumental record at the same quality and resolution of the instrumental record in ocean temperatures if we really try hard enough. So you can duplicate what I've shown with the fossil corals from the Line Islands at probably 50 different sites around the world. It's just a matter of how bad do you want that data, right? Because if you throw enough money at this problem, we could solve this problem. So to your other points about where these corals are coming from, these atolls are very steeply sloping. So they're kind of poking out of the ocean bottom like needles. And so the reefs that we work on quite purposefully are far away from kind of lagoonal inlets, which are often on the leeward side. And so we try to work at the places where the topography is just very, very steep. And so you're diving and it's like 10 feet over there is the deep blue and 10 feet over there is the breakers. And so when we find these deposits on the beach, we're fairly confident that they're coming from a pretty narrow assemblage of depths, probably like 20 feet to 40 feet. And indeed, when we dive today, we kind of see, we target the 30-foot isobath for all of our work. That's where we see the healthiest, most abundant, large-sized class corals.
Thank you for all that. A question about your conclusions about the increasing severity of El Nino. Does that apply to the extreme temperatures, or also the greater frequency of time?
So the metric that we chose is very sensitive to the amplitude of the variations. But I do want to say that what we can detect is a fundamental change in the properties of the phenomenon itself. So if we are seeing greater amplitude at our site, we have to think about 3 reasons why that could be. Number 1, the entire phenomenon could be increasing in potency across the entire basin, right? As a wholesale phenomenon that spatially extends across the entire basin. That would be one way to do this, and that would have the most probably important consequences. And then the other way to do it is to increase temperature just at our site by changing the spatial signature of the phenomenon, the loading of maximum sea surface temperatures closer to the Central Pacific, which is in fact what some models suggest and some of the instrumental data suggests, that there's an increase in the flavor of Central Pacific El Nino events relative to Eastern Pacific El Nino events. The Eastern Pacific would be more like 97, 98. In this 2015, 2016 event was closer to a Central Pacific event than before. So that could be that we just have, in my site, we're seeing greater temperature amplitude, right? That's a possibility. And then the third possibility is that, remember I talked about how a portion of our amplitude that's written into our coral record is caused by the hydrological response in precipitation evaporation, and its imprint on the surface layer, oxygen isotopes of the seawater, which is our starting point for growing a coral. And so if that component has increased in amplitude, then that also be an explanation, the increase in amplitude in the coral records that we see. And that would imply an increase in the hydrological component that is driven by an underlying El Nino temperature anomaly. And so that's also been supported by some recent modeling efforts that say that in a greenhouse world, all things being equal, your average El Nino event will have greater rainfall bang for SST buck. And so that's a possibility that we also have to evaluate. And so I can't determine which all from all these possibilities is occurring without going to other sites, other places, and trying to pile more evidence onto the heap. But these other studies from different places that we do have, and there are only like 3 or 4 of these kinds of studies from trees and all different archives, seem to point in the same direction. So whatever it is, it's probably not just related to my one site getting more amplitude. It's probably a fundamental shift in the wholesale properties. And that would, regardless of the answer of the other options, imply that we will have greater extremes written across the world, transmitted through a greater atmospheric response to the ENSO phenomena. That's a very long answer. Yeah.
So has any of this allowed you to make more specific predictions for what's going to happen in the future for the next El Nino cycle? And if so, is there any work being done to protect the coral? If you know a temperature spike is coming, is there any way to protect it from a temperature?
You can't get in front of that train. The scale of what you would have to do is impossible. So we knew this El Nino event was going to come 6 months before it did. We also knew 3 months ahead that it was going to be extremely large, and yet all of us just had to sit back and watch it roll out. And there's really nothing you can do to get in front of that. In terms of what it means for the future, I think there are a couple things to take home. One is the fact that even in this non-El Nino year, we have extensive bleaching across the Great Barrier Reef that's not related to El Nino, but instead related to the steady ramp of ocean temperatures. Well, kind of not very steady, but decade by decade it's getting warmer, right? That's going to be pushing coral reefs closer to an absolute bleaching mortality threshold. And so that's what I take away from my study combined with the Great Barrier Reef increase in bleaching frequency, is that we have a situation where an ecosystem is going to be knocking against a wall much, much more frequently. And so whether it's due to a rise in ocean baseline temperatures, and then if you have a superimposed kind of larger El Nino events spiking you towards greater values, you're going to be in for much more frequent bleaching and mortality events across reefs. And so, you know, I always get asked this for reports. What does this mean for long-term coral? Are they all going to die by 2050, 2020, Dr. Cobb? And nobody can answer that, other than to say that near-term warming in the ocean is inevitable. We have at least 50 years baked in of pretty aggressive temperature changes like the ones that we've seen in the last couple decades. So we can't avoid that, and corals can't avoid that. Those corals that are very susceptible to, that live closer to that absolute threshold of about 30 degrees bleaching, are going to be feeling the brunt of the damage in the next decade or two. And it's sobering for somebody who's worked on many, many different climate records and sunk their teeth into ocean temperature records from across the world. It's sobering that this event brought this level of destruction across the coral reefs of the planet. I think we were all just shocked as an entire community with the level of death that happened during 2016. And it really kind of pushed fast forward for us. What we thought was like 2030, 2040, 2050 reality is now, actually, like today, yesterday, last year. And so that's very sobering. I think it means that we're out of time for protecting some of the world's most susceptible reefs, including my own, that already has faced a hit that would take 30 years to recover from. But the fact that it's not going to have 30 years to recover. It's going to have maybe 5, maybe 10, maybe 15. That's not going to be enough. So they're going to take these hits until they're just a shadow of what they were like before this El Niño event. Take a step function and just kind of tick over into a different space. There will be reefs that will be reefs that are cold stressed in winters right now are going to become more favorable places for flourishing reefs of 2050. But this is like on the fly community level thinking, because we're just playing catch up with the acceleration of the reality of the fact. It's sobering. Yeah.
For decades, we were concerned about the future coral reefs as a consequence of the loss of accessible carbon.
Yes.
It seems the country should be running way ahead of the carbon effect. What do we know about the advance of loss of accessible carbon? This is also a result of certification.
Yeah, I mean,
Information those effects occur now, or just exclusively temperature and forecasting, because the carbon effect would affect temperature.
Yes, and so, this whole body of work is not my expertise in terms of the kind of tank experiments that people are doing to look at ecological function with reef interactions and reproductive cycles with acidification. But from what I can tell, there's obviously going to be a whole class of organisms whose fundamental ecological function is going to be disrupted in some key way, whether it's sensory abilities or prey capture. I'm not even going to try. But at any rate, that's what it seems to indicate, all that body of literature. But I think it was since projections in the last 5 years before this event happened, people were projecting that the temperature stress would come first to threaten some of the most vast global reefs that we have today. And they were projecting that like 2030, 2040. No, now. And so this El Niño event has really brought this home, that it's not just the steady ramp we have to worry about, it's the extremes, whether driven by 100% natural variability or dialed up themselves by CO2. It doesn't really matter if you're a coral. So I think that is going to come home to roost first, and that's what we've seen in this last couple of years. That's really what the evidence points to. And again, it's a catch-up moment for the community, and a very important calibration point for the community. Yeah, one more?
First of all, I was one of the 50 people at the AU rally in ceremony.
Yes, thank you!
I actually got interviewed by Chris and was not in the White Lab President. My question has to do with the linkage between this information and the type of ecological research that we are doing, because I'm seeing more and more people in our fields working on the needs of the floods and droughts. And I feel like that's getting lost a little bit below the radar.
Yeah, I mean, I'm not an ecologist, so I can't tell your stories. I can tell the story because it's my site, and I've been diving there for 20 years, and I see things with my own eyes, and I work with ecologists on my site who help me understand how that works at my site. But I don't know other sites, but I think y'all need to challenge yourselves to begin to tell these stories.
Should we be talking about the El Nino strengthening along with our talking about the drought so that we superimpose that better? I guess that's
So there is a whole report by the National Academy that just came out last month on what we as a community feel comfortable saying about the increase of climate extremes with climate change. So I refer you to that. I can send that to Nikki, and she can put that in the conference materials if you guys want. So you should read through that. But the idea that we have greater precipitation intensity and greater drought in drought-prone areas is becoming, I wouldn't say 99.9, but we're becoming, as talking points, very comfortable in pointing to a range of different studies providing that. So I would say that's part of kind of being informed about the latest advances in climate science, because if you wait until the next IPCC report comes out and you're only using the talking points from the last IPCC report, that's a day late and a dollar short. So I definitely encourage you to think about weaving in these pieces of emergent science and talking about these thresholding capacities and using some very prominent examples like the Great Barrier Reef or my own site or your own ecological systems that you work with in terms of illustrating what you've seen and how you interpret this body of information and what you think it does say about decision support and policymakers and opportunities and timescales and vulnerabilities.
Okay, that's all we have time for right now, but please give Dr. Cobb another round of applause. Dr. Fitzgerald to give a quick, very quick closing remark for EIS. Mr. Brown, for
I was delighted when the committee asked me to give closing remarks because I knew I would have an incentive to pay attention all day. And then I was thinking, man, like what if you had to give the closing remarks tomorrow after the student talks every death. But no, not really. I did that last year, but that was easy because I just stood up and made fun of Stuart Penn. But what an amazing lineup of lectures we've heard today from some of the most prominent researchers in ecology, conservation, social science, tropical ecology, climate change, landscape ecology. I loved all the talks, and I want to join in with all of us to thank the speakers for visiting us and sharing their experiences and insights. About the role of keystone individuals in a complex system, and certainly can relate that even in the seemingly small world of social spiders, we take lessons into the world we live in today, where one or just a few misinformed, furry-headed individuals can have unanticipated impacts on numerous facets of everyday life, especially if they stay in Washington too long and we follow them no matter what. We also learned how, despite an astonishing diversity of life that fascinates us and that makes us love our favorite animals, the inherited characteristics that are shared among disparate taxa can be boiled down to a generalizable, predictable pattern of ecological niches that probably has been repeated since as long as species have been co-occurring. We've also been reminded that we're not outside observers admiring the ecology, whether we're making periodic tables deciding who's a keystone or figuring out how, why, and how much the climate is changing. A big part of what we heard today is that we're all in this together in a complex SES, sharing, using, abusing, commandeering, and hopefully learning to adapt in order to sustain ecosystem services at every scale, from local to global. And we've even been reminded that the course of these interactions play out in real landscapes that are modified through society's actions. Some of these changes cannot be reversed, hence the Anthropocene. I'm sure I won't be the only one pulling all this together and thinking about it as we continue to reflect on the synthetic messages we've heard today. But before continuing for just a minute longer, I have a couple of announcements that I was asked to make. Tomorrow evening, please come party down at the Casa Fitzgerald, led by some accurately informed keystones in a managed forest setting. Don't worry about rain or where the rain has come from, if it's because we screwed up somewhere or something like that. The rain will be subsiding by the evening. But when you do come over tomorrow and park, please don't make ruts. Just park along the edge of the road. Otherwise, the committee will be out all weekend shoveling dirt and filling ruts in neighbors' yards. Most importantly, I want to congratulate the EIS committee this year, reminding all of us that the group consists solely of graduate students who decided 18 years ago to ask speakers to reflect on their research programs and bring their expertise to us. You speakers today are about the 100th prestigious ecologists that have come to the Ecological Integration Symposium over 18 years. Very impressive. The theme today, micro to macro in the Anthropocene. So the insightful thematic focus that was designed by the students not only inspired you, the speakers, but also makes us reflect on the challenges and opportunities that are confronting us, and especially them in their careers ahead. So congratulations to you all, you did it. The committee also asked me to remind graduate students that now is the time to form the EIS committee for next year. Next year will be the 19th consecutive EIS, and it's already time to get started. So get in touch with the current EIS committee, think broadly, seek advice from a large group in EEB, the ABS program in your departments and your favorite professors, and have fun doing it. Happy hour right now is at Rough Draft in Northgate. The speakers are going to be there for a short time because they all have dinner dates, I believe. So let's get over there ASAP. But please join me in thanking once again David Sines, Carol Arantes, Nikki Roach, Lauren Redmore, Jordan Rogan, Mackenzie Kildegard, Aline Freitas Spindola, Ali Abdullah Al-Badran, and Javier Jaime, and the speakers they brought to us. See you in a few minutes for a good conversation.